Thank you. Yeah, hope everyone can hear me well. So thank you very much again for the invitation and the very nice introduction. So I'm going to talk to you a little bit about kind of history of where things have come from in my research in particular, and then about some of the things I'm most excited about at the moment. Yeah, so I've been working in this area of SLAM with vision now for pretty much 30 years. So this is me as a young man. I think this was the day I submitted my PhD thesis actually at the University of Oxford. And we were working right back then on SLAM using vision, which at the time was still a fairly unusual thing to do. So there'd been people working on robots making maps, typically using sensors that weren't vision, sonar, other things like that. There was tons of work going on in computer vision on 3D reconstruction, but kind of putting those together and trying to run them in real time on robots was still a fairly new thing in those days, and we weren't sure how far it was going to go. So these were the kind of maps that we were able to make with that robot rolling around in the lab, so making these very sparse maps of visual landmarks and then estimating the robot's motion with respect to those. So this was detecting visual features and then running a probabilistic estimator, a Kalman filter to jointly estimate everything. So that was not particularly impactful at the time. A few years later, we were gradually trying to make this more generally useful and had a kind of big step forward with this method called monoslam. So this was published in 2003, and it was showing real-time monocular slam with a single camera. So we're just waving a camera around in a room. I'll just very quickly show the video. So waving a camera around, and the goal is to estimate the motion of the camera in real time and build a map of the surroundings. So in full 3D. But the map is very sparse. So this is what the camera is seeing. We're detecting and tracking naturally occurring landmark features in the room. And then we're building this kind of real-time map. So here's the camera flying around, its position being estimated 30 frames per second. And then this is the map of landmarks that it's building. And the landmarks are accompanied by these kind of uncertainty ellipses, which is kind of the internals of the Kalman filter. So you'll see landmarks get more and more certain the more times we observe them. And already back then we were thinking, what could be the applications of this? It could be robotics, it could be things like, wearables and AR, VR, stuff like that. And then of course tons of work built on that over the years. In the years since then, we've been interested in just increasing the quality of these representations that we can build in real time. So that kind of landmark-based representation is good if the only thing you're really interested in is the motion of the camera. So a sparse landmark map enables localization. But if you're interested in actually doing more intelligent things in the scene, you need to capture more information. So we went through steps of trying to reconstruct dense geometry. So this was around 2010, 2011, systems like DTAM and Connect Fusion, some of them using depth cameras, some of them using passive cameras, and starting to investigate how you could really get detailed geometry. So important technologies feeding into that, GPUs started to become usable as generally programmable processors that allow you to really do the sort of level of processing to do this kind of thing in real time. And in depth cameras were another technology that came out of the gaming industry around that time. And then the other kind of thing that's always been of interest is trying to add meaning to those maps. So maps that aren't just geometry but also have semantic information. And in the limit, I think what we're always trying to do there is build maps really of objects in scenes. So this was SLAM++ from 2013, which was a system that made the rather strong assumption that we had CAD models available of the objects that we expected to see in the scene. And so we're kind of directly recognizing those objects and directly building a 3D map at the level of those objects. So you could think of this a bit like MonoSlam, but instead of landmark patches, we have objects like chairs, and those are the units of our map. So, it's a very accurate, complete, useful representation, but with the limitation that you have to know about the objects in advance. So, in recent times, in my lab, we've still been trying to build, I would say, systems a bit like this. So real-time systems, ideally that just use a single camera flying around as the input, working in real time, and the goal is to build a representation of the scene and then actually track the camera against that representation. So of course, in recent years, we're able to make use of strong information that can come from pre-trained neural networks to feed into this kind of estimation. So I'll show you a couple of examples there. So this is a system called Super Primitive that we published last year. So here we've got a single camera stream of video. We're running two types of neural network on that input stream to kind of give us some good prior information. One is that we are segmenting the input stream using an off-the-shelf network, and the other is that we're predicting local geometric information here in the form of a normal map. So let me just show you quickly how this works. So we've got input images that come in. We're segmenting them into chunks that we think are approximately objects, and then each of those objects we're predicting the normals across it. So here's an object that we've segmented. I think this is a bag or something that's leaning against the wall. We've got pretty good segmentation, and then within that segmented region, we assume that the normal field is continuous, and therefore you can integrate up the normal field to estimate the local shape of that object. But what we are not assuming is that we've got an accurate prediction of its kind of size and depth. I mean, that's something a neural network can try and do, but is often unreliable. So we assume that we are uncertain about the scale and size of this object. And how close it is to the camera. So basically, we've got this one-dimensional ambiguity in a single image of, is this a small object that's close to the camera or a large object that's far away? But then, of course, we've got more images. So we've got a moving camera, and we are observing this scene from multiple viewpoints. So therefore, we project each of these sort of hypotheses of the depth and scale of this object into the other views, and then we optimize, and we say we'll choose the one that is most photoconsistent. And we do that for all of the objects in the scene, and we can get this quite nice reconstruction. The local geometry quality is very good, and it's segmented into objects. So let me just skip forward to some more kind of complete examples. So we build this now into essentially an object-based SLAM system, which again, in my mind, has the same kind of character as MonoSlam or SLAM++. It's a map made out of chunks, but now the chunks are these quite arbitrary objects, and we can run it on all sorts of different scenes, indoors or outdoors. Let me just show you some slightly different examples. Yeah, because these are powerful pre-trained networks that have seen lots of data, they work in all kinds of different scenes. So this is a system that uses these fairly strong single image priors. Something else that we've done is build on this amazing work master coming out of NAVER Labs Europe. So this is a system called Master SLAM that we published this year. So this is a real-time single camera SLAM system that uses the two-view prior that we can get out of master. So essentially, as Martin explained, master, you can feed in two images. As long as they're reasonably close together, master will output a 3D point cloud that uses information from both of those images. So it does this amazing thing of both kind of taking advantage of single view priors, but also matching information between multiple images to give you a much better local 3D point cloud than you can get from just a single image. So in Master SLAM, we've got this camera continuously running around. We're taking pairs of images, building these local 3D point clouds, but then using SLAM-like methods to stitch all of that together in real time into a consistent 3D map. So this graph that you can see here is a set of keyframes that we have selected, each of which has its local geometry, and we're kind of stitching all of that together into a coherent, consistent 3D map here, which can, you know, grow over time. It can run on arbitrarily long image sequences, and again is very flexible, can work in, you know, lots of different sorts of environments, indoors and outdoors. If you've been to Imperial College in London, you'll recognise the Royal Albert Hall, which is just near to where we work. So, okay, so you know, Visual SLAM is this technology that people have been working on, and I would argue is gradually getting better, more interesting, more representational. So, of course, Visual SLAM in various forms is already out there in a lot of different types of products. So these are just kind of consumer products. Of course, it's doing lots of other things in industry and different areas. Some of these we would definitely recognize as robots. So things like robot vacuum cleaners, or things like drones are commonly running Visual SLAM. I think what maybe not everyone knows about is, you know, this technology is also used a lot in other products. So things like headsets, you know, for AR and VR. You know, many companies make amazing devices, but just a little example here from one of the ones from Oculus, which is now Meta, of course, just showing, you know, how do these devices track their position in the world in order to perform virtual reality or augmented reality. They're using Visual SLAM these days. They have cameras built into them, and they're making these feature-based maps of the world, and that's how they do really accurate positioning. So it would be, you know, these products are really interesting. I think it would be fair to say that these are all still kind of early products. I'm not sure they're really changing the world too much yet. So what are the products that might actually do that? What are the products that people are really dreaming about? I think we'll hear a lot of talk in this workshop about, you know, general robotics. So let's imagine, you know, this robot that could really come in and, you know, tidy up your room, clean your kitchen. This is a really famous old video from about 15 years ago of a robot apparently doing really general things in the home. This is, of course, is a fake video in the sense that it's teleoperated by a human. I think we're starting to see videos of real robots now that start to get a little bit close to this, but still I would say with nothing like the full flexibility and reliability that would enable, you know, robot products that people would really imagine will change their lives. You could just reliably ask this robot to tidy up your house or something like that. I think another category of product that could be really important is, this generalization of wearable smart devices. This is a picture of Meta's Project Aria. So it's a prototype of really lightweight smart glasses that you would wear that would have kind of always-on spatial intelligence, understanding everything that's going on around you and providing you with all sorts of information that you needed. So these products are still really, really tough, and my kind of guess is that these products are still several years out until they really become practical. Partly the sort of vision, AI, and everything we need to do them, we still don't know how to do it. But I would say when you take into account the actual constraints that products like this would need to fit in to really become successful, of things like size, weight, power usage, cost, safety, these things are even further out. I mean, having worked for years on robot vacuum cleaners and understanding just how hard that has been, and if you own a robot vacuum cleaner, you still probably find it annoying in certain ways. It doesn't really do everything that you'd want it to do. And that's 100 times easier than products like these. So I think we're still going to be doing this kind of thing for a long time yet. So that gets me onto this kind of, arguments. I called my talk from SLAM to spatial AI. Where are we with all of that? What does spatial AI mean? So my kind of definition, so when I first started using this term, so in this paper from 2018, I defined spatial AI as the online problem where vision is to be used, usually alongside other sensors, as part of the AI which permits an embodied device to interact usefully with its environment. And so my argument in that paper and since is that, you know, spatial AI is about kind of understanding the scenes around you, building representations in a way that enables intelligence. And this argument that the work we've been doing in SLAM has always really been about that. It's always been about building representations that enable robots or other devices to do intelligent things in the scenes that they're in. And you know, SLAM has always had that character of doing the best you can with the information you can acquire, with the sensors you've got on board, taking advantage of priors if you've got them. But you know, this real-time character, this map that always updates as you move around and change things, in my mind, that's still a good model for what we should be trying to do in spatial AI. So hence this argument that SLAM is kind of evolving into that. I just want one thing to mention. There's a new book coming out called the SLAM Handbook, which I and many others have contributed to. It's free, available free online already, but it will also be available as a printed book soon, which has a lot about the history of SLAM and also kind of recent things that are going on there, and this evolution into spatial AI. So, you know, another kind of big question at the moment, I think, is, so I've mentioned representation already several times, but, you know, there's a lot of people wondering, if you want to do embodied AI, if you want to do robotics, what do you need representation at all? Or if you do, what type of representation should it be? So you'll see lots of companies out there at the moment with this idea of, you know, you might call it foundation model for robotics or for AI. So this idea that if you want a robot to do intelligent things like tidy up a kitchen, you just show it loads and loads of examples of robots doing that thing. So you capture data, maybe you do it by teleoperating robots, maybe you do it by, you know, wearing some smart claws and doing kind of actions, or maybe you do it even by watching YouTube videos of humans doing tasks. And eventually you learn this mapping between images and actions. So this is the thing that I see, and these are the actions that I take, and that's all kind of encoded in a neural network that just runs kind of end to end and doesn't explicitly kind of build like anything like a map or a representation. So, you know, will that work? Maybe it will eventually. You know, I think already in domains like autonomous driving, you know, I think we're going to hear from Wave later in this workshop. You know, they've got amazing progress on that kind of approach. How far will that take us towards really general intelligence? So I think the alternative is to say, you know, we need some kind of explicit representation of scenes. And I think this is also a really interesting discussion, a sliding scale. What do we mean by representation? So if I move a camera around in this room and build a representation of it, I think at one end, you've got this idea of a pretty explicit representation, which I would say is the more direct continuation of the SLAM work that I've shown you. It could be something like a scene graph of all of the objects in this scene, you know, their positions, their physical properties, you know, weights and masses and friction. But it could be something like the sort of the model that you have in a video game that represents, you know, a level that you're designing. At the other end, it could be something entirely abstract. So maybe this term world model that's being used in machine learning these days, I think means this ability to represent a scene in a sense that will enable you to predict what will happen next, but where it's not necessarily a human understandable scene graph. It's just some vector of tokens in a neural network somewhere. So, you know, to be honest, I'm quite agnostic about which of those it could be. And in the end, it will probably be somewhere in between. I mean, the properties we want of a representation, it should be accurate, it should be efficient, it should be composable, you know, it should be editable. Probably in some sense it should be understandable or you know, human interpretable. It should be able to be communicated between different devices. All of those properties, you know, I think may lead us back towards something a little bit more explicit than a purely abstract world model. But anyway, this is ongoing research, and neither of these work yet. None of us know how to really do general embodied AI. So I think there's going to be plenty of interesting research. So something that I'm really interested in, independent of exactly what that representation is what I would call the computational structure of spatial AI. So what I mean by that is, this is just a rough sketch of the sort of system diagram of one of those SLAM systems that I showed you earlier. They're pretty complicated things, but some of the key characteristics are, we've got a continuous incoming stream of data from cameras, but possibly from also other sensors. We've got things like neural networks operating on some of that. We've got a long-term representation, a map or a world model that's being kind of updated. So there's always new data being fed in, that's being updated, it's being used to make predictions. It's complicated, and it has this sort of loopy nature. It has the character where certain parts of that should be kind of stored and updated. So what I mainly want to get across is I don't think it's just like an end-to-end thing where you feed data in and outputs kind of come out. It has this kind of loopy character. So the other thing that I'm also always thinking about is where are we with the actual hardware that this is going to run on. So if I look at current lab implementation of something like this, it's running probably on a big desktop or laptop system. It's got CPUs and GPUs doing different things, memory in different places, lots of stuff flowing around. It's quite expensive actually. So how are we going to make a system like that very efficient? That's a really important thing if we want to make it run on small embedded platforms. And then what predictions can we make about the hardware that this is going to run on? So we've seen this kind of move already from CPUs through GPUs as the dominant hardware for AI, but I believe that's just the beginning. And we're going to see more and more kind of interesting innovation in this space of processors for AI, and in particular, specific processors really designed for vision and AI. And my kind of prediction is we have to embrace parallelism. Clearly, we can't just run CPUs faster and faster, but the type of parallelism that will be coming, I think, will be a bit different from what we see on GPUs. Where you have all these cores that have a kind of flow of memory through them and are basically all doing the same thing. I think we'll see more sort of general distributed parallelism, and in particular, this kind of move towards memory and processing being co-located. So the thing that's really expensive in computation is moving data around. That's the thing you want to minimize. So I think eventually, maybe this is more brain, but essentially we'll have many processing cores, each with local memory, and then kind of communication between them to keep everything kind of synchronized. But as far as possible, you want to avoid moving big chunks of data around. And I put this in kind of as a joke, but we will laugh in a few years at what we're doing at the moment. It's a little bit ridiculous, these huge, data centers and, gigawatt stuff. When the brain can do it in 10, 20 watts, we will get there eventually, and it will, we've got to keep our eye on, what's going on at the moment is just a point in time, this kind of GPU world. We will get past that into something else. So one of the things I've been doing is working with, one of the things we've been doing is working with companies, you're thinking about and developing new processors. So there's a company in the UK called GraphCore that do actually develop these type of processors that have many processing tiles on one chip. Each one you can think of as like a little CPU, really, with its own local memory, and then lots of high bandwidth communication and high bandwidth memory on the chip. So if you want to run algorithms efficiently on that, you think about the computational structure of the algorithm, and you almost kind of map it down geographically onto the processor. So this is one of their visualizations. So in spatial AI, I've been thinking a lot about how we would think about, the representations, the computational patterns, the storage patterns in a spatial AI, and how you would actually kind of map that down pretty much geographically onto a processor. So once we are thinking about this type of computation, where in general I think we want graphical structures of our algorithms and our data structures, and as far as possible we'd like to do computation kind of in place on those structures. It takes you back to thinking about the algorithms that we've always been using in SLAM, which have always had this graph-like structure, and in particular there's this probabilistic graphical model formulation called the factor graph, which is the kind of key thing that we always go back to in SLAM. So you think about what are the things I'm trying to estimate and what is the information I've got. So in SLAM, for instance, our factor graph might look something like this. We've got the things we're trying to estimate, which are the trajectory variables of a camera that's moving around and the positions of the landmarks it's observing. So these white circles are the things we're trying to estimate. The black dots here are the things we can measure. So these are things like measurements from a camera or measurements from maybe an odometry sensor. These give us constraints on the relative values of these variables. So I've been thinking a lot about what sort of algorithms can do in-place computation on these sort of graphs, and I've been led back actually to some quite old types of algorithms. So in particular belief propagation and this variant Gaussian belief propagation, which has this property of being able to do inference on factor graphs via local computation and message passing. And this may just be one of a whole family of algorithms that have this kind of property, but in particular Gaussian belief propagation has some properties of distributed convergence. There are actually some proofs of how distributed computation can be done here. So I'm just going to quickly show you a little demo of this. So we have an online article called A Visual Introduction to Gaussian Belief Propagation, which you can go to at gaussianbp.github.io if you're interested. So it's got various built-in demos, of which I'll just quickly show you a couple here. So let's think about a very simple problem here. We're basically trying to fit a line to some points. So what we're trying to do is estimate the height of the line at these locations here where we have these blue variables. So we're going to do that by basically solving a factor graph that looks something like this. So the blue variables are the things we're trying to estimate. The red squares here are our factors or constraints. We want our blue points to be close to the red data, and that's these factors enforce that. We also have a smoothness prior. That means we want the whole line that we're fitting to be smooth. So here we're going to solve this by belief propagation. So if I click this button, we're going to pass messages along this graph from left to right and then back from right to left. And so in this simple graph here that has no cycles, we can get to the optimal solution simply by passing messages all the way one way and then all the way back. But if I just clear it and run it again, now we can simulate something like a distributed setting. So imagine that each of these variables was now stored on a different processing core. We can now process this in parallel. So a little bit of local computation at each one of those blue nodes and then some message passing, iterate that a few times, and we can get to this same solution. But even more interesting, we can do it with a random message pattern. So if I just click this button a lot of times, every time I do this, a random variable is passing a message in a random direction. So Gaussian belief propagation has this property that even with asynchronous random message passing, we can still converge to the same solution. So in my mind, this is the kind of computational pattern which I think will fit this hardware in the future. And this applies to much more complicated problems. So this is like a bit like a multi-robot pose graph type problem. You can run it in multiple dimensions here. There's another nice example down here. This is applying it to an image processing type problem. So this is actually a very similar formulation to what has often been done in computer vision. But suppose you want to remove the noise from this image. So we've got an input image. It's got some noise in it. We formulate a factor graph that says I want to estimate a denoised image which is close to the input image. So these are these red factors here on the blue variables saying be close to the data, but also with a smoothness property. So this is an MRF type of formulation expressed as a factor graph. As I turn up the smoothness precision, so we've got Gaussian bleed propagation running continuously in the background here, just running on my laptop solving this. As I increase the smoothness, you can see that if we use a standard Gaussian model, we can remove the smoothness, but at the cost of blurring the whole image. We can run with a Huber kernel, so this is like a robust kernel, which means that every time we pass a message, we're sort of checking how much do I think this is a feasible message, and down weighting it if it seems not too likely. And then as I increase the smoothness, you can see we get this lovely kind of edge preserving smoothness going on, where we can remove the data, remove the noise, but not destroy the edges in the image. Okay, so you're welcome to play around with that if you're interested. So yeah, these kind of distributed algorithms, we've tried various things with these algorithms. So in computer vision, we implemented bundle adjustment using this algorithm. So on GraphCore's graph processor, showing that. So bundle adjustment is this classic problem where you've got cameras and points, and you're trying to estimate the positions of the cameras and points by minimizing the energy of the constraints. You essentially take the factor graph for bundle adjustment, you map it down onto the tiles of a graph processor, and then you solve it by passing messages around. So you need to do more iterations than you would in a standard batch solver, but very, very distributed computation that can be very efficient and fast. What becomes maybe even more interesting though is when a problem becomes more complicated. So this is something we looked at that I think is the sort of thing we're interested in spatial AI. So we might start with a point-based model of a scene, but we gradually want to abstract that into something that's more like an object-based model. So here's a factor graph just for cameras and points, but then we might start to make some hypotheses like, oh, I think these points here look like they're all lying in a single plane. So I'll introduce another variable here that represents the parameters of a plane. I'll introduce factors that kind of say this plane should lie within these points. And then I'll just keep passing messages around. And at some point, I may become sure enough about this plane that I'll actually remove the points and just represent the plane directly. So my point is, in normal factor graph terms and normal estimation terms, this would be pretty complicated. You'd have this big kind of matrix that you were trying to invert. You'd have to keep changing the structure and finding the sparsity. With a local belief propagation method, you can do all of this locally. You just keep passing messages around, and methods like this can potentially work. So this kind of in-place representation that's sort of simplifying itself locally seems to have the right kind of properties. The most recent thing we're working on in this sort of area is on-sensor vision. So this is actually a collaboration with a couple of other universities in the UK, especially the University of Manchester, where they have these prototypes of vision chips that have processing built in. So it's like an array of pixels where every pixel has a little processor built into it, the ability to receive light and then do some computation, exchange information with its neighbors. So how much computer vision can we do actually within the pixels? They've already shown some pretty impressive things with these sensors, but we think we could potentially do full kind of optical flow, dense geometry estimation. You can also run small CNNs on these kind of processors, but with sort of belief propagation type of algorithms running in the pixels, we think we can do quite a lot there. So that's ongoing research. And yeah, so I should say, something else that we think is really feasible here is, so the factor graphs that I've talked about so far, these are hand-designed models, but can we put more kind of general learning structure into those factor graphs? And I think we can. So we've got some general, initial work on that area published last year to say, rather than having factor graphs as one thing and neural networks as another, can we actually design learning structure directly into factor graphs with these same properties of being able to compute in a distributed kind of in-place way? So that's quite preliminary, so I won't go into it much yet. The thing I'd like to talk about for the last few minutes is a relatively new interest of mine in robotics, but which I also think is very important. It's so multi-robot or many robot systems. So let's imagine an application of the future. So this is just something I found on the internet somewhere, but something like a smart farm of the future. And this could be representative of many types of application areas. We expect that things like this are going to get a lot more automated, but also there will probably be many different types of automation. So maybe in a smart farm of the future, there'll be some wheeled robots that are moving around, attending to the crops. There'll probably be some flying devices that might be surveying things. There'll probably also be humans involved who will be carrying some, wearable computers or something. So how are all of those things going to interoperate? How are they going to work together? So one obvious possibility is that all of them will need to talk to the same kind of global cloud provider. Maybe the future instantiation of current maps type systems. All of these devices will talk to that. And so problems like how do they all localize together in a space? How do they all plan their motion so that they don't crash into each other? So that is definitely a possibility, but maybe there's another possibility which is a bit more decentralized. So I guess maybe an ideal situation would be any company could make, a device that would operate, do some job on a farm. And then if it obeyed some kind of common open protocols, perhaps, then it would be able to interoperate with all the other devices. That would seem to be a desirable thing. So we've been thinking about this kind of problem, and especially initially focusing on a couple of areas. The most important immediate one is localization. So how would all of these devices be able to estimate their positions within this global space on the assumption that they have distributed computation? So here we've taken this assumption that we're solving this pure multi-robot localization problem. So we have 3 robots here in this example. The things that we're trying to estimate are the positions of each of those robots over a set of time steps. So robot 1, these are its position variables as it's moving. And we're assuming that that robot has a local ability to estimate its motion. So that's represented by these factors here. This could be wheel odometry. It could be some local form of visual odometry or something. But also it can co-observe other robots in the scene. So we also have these factors that connect different robots. And this is like one robot observing another. So at this time step, actually this robot observed this one with its sensor, but also this robot observed this one with its sensor. So this is the full factor graph from that. And of course, if we had all of that information and we uploaded it to some central server, we just do inference on this factor graph, send the information back to the robots, tell them all where they were. But what if we wanted to do it distributed? So we can actually solve this with Gaussian belief propagation in a distributed way. So the way we do it is we take this whole factor graph and we basically divide it up. So we draw these dotted lines around parts of the factor graph. And so each robot stores just part of the factor graph. So the green robot will store the part inside this dotted line. So that is stored on this robot's processor. The parts of the factor graph inside the dotted line, it passes messages around that and tries to bring it to convergence. But also it wants to pass messages, across these dotted lines. So obviously this has to be done by communication. So the robots have to talk to each other. But the really, nice point about belief propagation, it has this asynchronous property. So this does not have to happen at the same rate as the message passing inside the fragments. So actually what each robot does is present, we call it a robot web page, which is basically all of its latest outgoing messages are presented on something like a web page. And then whenever one of the other robots can be close enough to be in communication, they can download each other's robot web pages, just get all the latest messages that cross those dotted lines. And that actually works very well. So I'll just show you a quick demo of that. So this is running on my, where is it? Sorry. So this is obviously a simulation of a true distributed system that's running here on my laptop. we've got a situation here which is, it's 30 robots that are all trying to drive around in circles of different radii. So there's a lot going on here, but basically if I just turn this off a second, you can see here the robots driving around in 2D. Now the robots are measuring each other. So here is the measurement pattern. So we assume here that each robot has a range-bearing sensor that can measure the distance and the angle to any other robots that are within some certain radius of it. In the corners here, we do have 4 fixed beacons. So these are to kind of anchor the coordinate system of the whole thing. These are 4 things that all the robots know where these things are. But you can see that only the robots with this kind of large radius ever get close enough to directly make measurements of those. Most of the measurements, most of the robots on the inside are only ever observing each other. But then behind the scenes, we're running message passing and belief propagation on all of that. So you can see all of the robots are actually in quite accurate positions. So to prove that, if I temporarily, I'll turn the range of the sensor down to 0. So this means that for a moment now, the robots are not getting into any inter-robot measurements. And now you can see that actually each robot, there's actually 2 things here. There's a ground truth position and there's an estimated position. And those tend to drift apart when they're not making any observations of each other. If I turn the sensor back on here, they'll now start to observe each other again and go back to accurate estimates of their positions. And so this is in fact a very robust system. Let's just go to this mode and very scalable. So this is with 100 robots. Let me just change a couple of things here. So I'm going to run with 100 robots and I'm actually going to put quite a short distance sensor here. So now that you can see that the pattern of interconnectivity between these robots is, quite local. It's changing all the time. And so basically we're running inference on this factor graph. That would be incredibly hard to do actually in a centralized form because we'd have this structure that's changing all the time. But here we're just following the local rules of message passing. Every operation is local. And we've got this kind of web of robots that all know their positions just by making local measurements. Okay, so I'd better finish up because I think I'm running out of time. Just get back to the slides. Okay. Yeah, so just to finish up, so spatial AI research, I think we're going to be doing it for a long time yet. Some really important topics. If we think persistent scene representations are important, what is the right form for those scene representations? What are the right representations that will, have these properties that we really need? They need to give us accurate kind of predictions of what's going on in the world, but in ways that are efficient and composable, and eventually, to give us this ability that I think humans have to sort of just drop into any scene and in a relatively unspecific way, make predictions about what will happen. If I pick up this object and use it to manipulate this object, what will happen? Humans can do that in a really kind of creative way. How will we get robots that can do that? So really important research issues, I think the computational patterns of representations and algorithms and how those will relate to what's going on in changing hardware. That's really important. And then in multi-robot systems, how could we really move towards interoperability, ideally between systems made by different companies? And we call our work there Robot Web because I think we're inspired by, what happened with the World Wide Web in computers. Is there something like HTML, HTTP for robotics, which could really enable this very flexible interoperability? Okay, I'll finish there. Thanks very much.
Thanks, Andrew.